Interval notation is an alternative strategy for writing inequalities. We can use this for any inequality that we want to write, including the solutions to inequalities that we solved. Let's start with a basic inequality, something like x is greater than 3. We know, if we want to represent the infinite number of solutions to this inequality, that we would place it on a number line and we would shade to the right. We're representing all of those numbers that are greater than 3. But this inequality is actually a simplification of the more proper way to write the solution inequality. Because this list of numbers is infinite, it's actually considered to be a set. And when we write a set, we use braces. We begin by identifying the set of numbers to which x will belong. This symbol means that x is an element of, x belongs to the set, and that symbol that looks like an R with a line in it, is the signifier for the real numbers. So what that actually says is that x is an element of the real numbers. When we write this inequality in true set notation, we then follow that designation of the set with this line. That line separates the inequality itself from the designation of the set. That line is read as such that. So we have x is an element of the real numbers such that x is greater than 3. That is the true proper way to write the set notation version of this inequality. Now, that is a lot to write to represent a fairly simple idea. Interval notation hopefully peels back all of those layers and instead worries about being able to give the information quickly and efficiently. Interval notation uses parentheses, brackets, and commas to represent the entirety of the solution space. The interval notation for this inequality looks like this. Now, before you think that looks like a point, like an XY point that you would find in space or on a line, this is an alternative use of parentheses and an alternative use of the comma. The first number we write is the lower bound of the region. The second number we write is the upper bound of the region. The lower bound of the region, the number 3, is where the graphing starts if we're looking at it from left to right. The upper bound of the region, this thing doesn't have an upper bound. It just goes on forever. So we represent that by using the infinity symbol. So we have 3 different ways to write inequalities. We have the overly simplistic way that you've been using since you started studying inequalities with variables. We have the actual proper set notation way, which uses the idea of elements and set notation as this is a set of solutions. And then we have the interval notation way that hopefully takes all of that information and shortens it so that you don't have as much to write and as much to worry about. We want to get to the point where we're comfortable jumping between the 3 of these, and at the same time, understand that certain situations might dictate that we use certain ones. There's no guarantee, for example, that in a problem that you have to be in the real numbers. If you're talking about something that requires use of the whole numbers, maybe you want x to only be the whole numbers. And so you would want your answers to be, if we're greater than 3, something like 4, 5, 6, 7, and not have all of those decimals in between. The real numbers don't worry about that. The whole numbers would. Let's try another one. And you can see what this looks like. Our next one is going to be we'll use y. Y is less than or equal to -4. So here's -4. We graph to the left, and that's what it would look like. That's a very pre-algebra, Algebra 1 kind of understanding. Let's try to do the set notation for this one. Y is going to be an element of the real numbers. because it's all of the numbers that are less than -4, such that y is less than -4. Really, this set notation, the only thing it's adding in is, yeah, it adds in the braces, but it really only adds in that designation that we're looking at all of the possible numbers. Now, we're again going to write this as lower bound and upper bound. Our lower bound here, we don't have one. This goes on forever to the left. So our lower bound is actually -infinity. Our upper bound, our highest place, is -4. Now we need a way to demonstrate that -4 is actually included in the solution space. See how I've filled in the circle? We have the equal to, we have the equal to. We didn't have that up here. We need a way to show that -4 is in that space. And the way that we do that is by using a bracket. So as strange as it looks to have a parentheses on the left and a bracket on the right, interval notation needed some way to show us that -4 was included. That's the way that you show that -4 is included. So very similar setup, very similar idea, still graphing on the number line. We're still an element of the real numbers, but we want to show the fact that we're going to stop at -4 as our upper bound for our solution space. Okay, our next one we're going to try is actually a compound inequality. We're going to go between the numbers 4 and 8. So we're including 4, we're including 8. Here's 4 to 8. Our set notation would be x is an element of the real numbers such that x is between 4 and 8. Again, no different than what we wrote over here. We're just including this. We know it's all the real numbers. It's not just the whole numbers. It's not just irrational numbers between 4 and 8. It's everybody. And then we're again going to use our lower bound, upper bound idea. So our lower bound for the region, the solution space region, is 4. The upper bound for the solution space region is 8. And we need to include both of them. So we use brackets instead of parentheses. Similar looking example here, where we're going to go from -4, which is included, up to 0, which is not. Same set notation. We're in the real numbers in between 0 and -4. Our low bound is -4. Our high bound is 0. We're going to include -4, but not include 0. And again, as strange as it looks, that's what it would look like. It's okay to have a mix and match of parentheses and brackets. You're going to need to do that to depict which one of those numbers would be included in the sample space. All right, for our last one, we're going to do another compound inequality, but this time we're going to bring in two inequalities going different directions. So we're going to have x is less than 6 or x is greater than 9. So here's less than 6. Here's greater than 9. Same thing as before. X is an element of the real numbers such that x is less than 6 or x is greater than 9. Nothing new there. But when we go to the interval notation, we have we're in a kind of a tough spot because we normally have an upper bound and a lower bound. I can't just say -infinity to +infinity because I have all of this space in here where there are no solutions. So if I said the lower bound was -infinity because the left side points all the way off to forever, and I said the upper bound was +infinity because this side points off all the way forever, that's not going to work because I have this dead space in the middle that goes between, I guess I did -6. So for the sake of conversation, let's change that to -6. I have this going from -6 all the way up to 9 where there's just nothing happening. There's no solutions in that space anywhere in that space. So how do we get around that when it comes to interval notation? Well, if I only gave you this, you'd be able to do that part. And if I only gave you this, you'd be able to do that part. The left part looks like that. The right part looks like this. and I need some way to join them together. The way that we join these two together is by using a symbol that looks like the letter U. So it might be a little bit hard to see how to write that, but it would look like this. We have a U, and then we have the other inequality. This is a representation for the word union, which literally means for us, put together. So it's saying put together the one on the left, the negative infinity up to -6, with the one on the right, the 9 up to the infinity. And when we union those two together, we imagine these two sections both being part of the solution. That leaves out the part that we don't want that's in the middle and just keeps the parts that are on the outside. So we're going to use this union symbol anytime we need to join together two separate inequalities that make up the solutions together.